YouTube channel. My name is Alison and I am one of the science teachers here. I'm going to be going over the history of the atom today, which is actually one of my favourite topics. It comes up in physics and chemistry, and if you're doing combined science, it's in the physics and chemistry subject content for those as well. I'm also going to be giving you a tiny sneak preview of the new content that's coming to the platform very, very soon, and I am super excited to be able to show you that. So this particular video is going to be suitable if you are already familiar with the models of the atom, and if you want to brush up, go back over the timeline, see how the models developed into each other over time. If this is the first time you're coming at the topic, don't worry. It's just going to be a little bit quick today, and there's an awful lot of information to take in. However, in the new course on Century, all of the models have their own video and their own sets of questions so that you can spend a little bit more time, go back over things as needed. Also, once we're done here today, you will be able to pause this video, go back and replay it, go over parts of it, and as you need, whatever you need to do is absolutely fine with this. I'm also going to go over some exam questions, the kind of typical ones you might see in this, so it's going to be useful for revision. Okay, let me just change this. So just before we get started with the lesson today, I just want to introduce Century if you are not already familiar with it. So while all the schools are closed, we really want to support you with your learning. So there are hundreds of maths and science and English videos and lessons available for you on the platform. Guardians, if you're watching, you can sign up at the link here, so century.tech/parent sign up. If you are over 13 and a student, you can sign up yourself as well. Don't worry about writing this address down right now. We're going to stick it in the description for you, and I'm going to show this slide also at the end of the video. One of the best things about Century is that it uses artificial intelligence to track your preferences for learning, your areas for improvement and your strengths, and then it personalises your learning journey for you to make sure that you get the absolute best you can out of this platform. So we're also running live lessons every single day, so have a look at the YouTube channel schedule to see what is coming up and if anything interests you. So I am going to move to the lesson now, and let me just have a look at this, and I'm going to take my face off. Okay, so first of all, let's have a think about what a model actually is. Not this sort. We're interested in scientific models today. So a scientific model is a way of explaining something that is too big or too small or too fast or too slow or too complicated to observe directly. This diagram here, so this is showing the scientific method. In order to find out about the world, the scientists will follow these steps. So first, we must make some kind of interesting observation, notice a problem to solve, and then once we have that, we'll develop a scientific question. After that, we'll develop a hypothesis. So a hypothesis is a proposal, which is a suggestion, intended to explain what we have observed. After we have our hypothesis, we will make a prediction that's based on the hypothesis. So the prediction is a statement suggesting what's going to happen in the future. Then we're going to collect data, we're going to analyse it, and we're going to evaluate and make some conclusions. So if our data doesn't support the hypothesis, we can go back to consider what other hypotheses there might be that explain whatever it was that we saw. If our data does support it, however, it can be accepted and it can be put towards a larger body of evidence for a scientific theory to develop. If all the evidence gathered by many scientists supports one idea, it will be accepted as a theory. So theories have been tested over and over again and they still hold. So when people say something is just a theory is never just anything. Theories have been tested so many times by so many brilliant minds, there is nothing that is just about them. I might have a small bee in my bonnet about this. But having said all of that, they are never actually accepted as fact. So if new evidence comes along, that can't be explained by the currently accepted theory, then the scientific method of creating the hypothesis, testing it, starts all over again. So one of the most well-known examples of theories and models changing over time as new evidence emerges is that of the atom. So here we have a timeline of the models of the atom. We are going to start with a mathematician and scientist called Democritus, and he proposed that if you cut something in half, and then in half again, and again, and again, and again, and again, and again, there would come a point where you couldn't cut it into anything smaller. So he called these particles atoms, that's from the Greek for uncuttable or indivisible, and he said that everything was made up of these. So his theory, he believed that all matter is made of tiny solid particles called atoms, that atoms cannot be divided, atoms are indestructible, and the shape of the atom explains the properties of the different elements. Okay, so if we move to the next one, John Dalton. John Dalton used the work of other scientists and evidence from his own experiments on gases to develop his atomic theory of matter. So he presented this in 1803. All matter is made up of tiny particles called atoms. Atoms cannot be created or destroyed. All atoms of an element are identical. The atoms of different elements have different sizes, colours, and masses. Atoms can join together to form larger particles called compounds. And atoms cannot be divided into anything smaller. Okay, so let's move on to the next one. So J.J. Thompson used the work of other scientists and evidence from his own experiments on gases to develop his theory. It's called the plum pudding model of the atom. He never actually called it the plum pudding model. It was the media at the time. So a plum pudding is a little bit like a Christmas pudding. If you've never had one before, you've never seen one before, it's kind of like a heavy sponge cake with sort of dried fruit inside of it. So he thought that the sponge part was like the positive charge of the atom, and the electrons were like the fruit that was sort of dotted through the pudding. So this is an important point I just want to cover now. All the models are 3D, so they're often shown in 2D diagrams. So nice and flat, it's easy to see, but they are in 3D. So the plum pudding model is a solid ball of positive charge with the negative electrons embedded randomly in that positive charge. Okay, so let's have a quick look at the kind of question you might see. So Thomson's experiment showed that atoms contained negatively charged particles. Why must the pudding part of the atom be positively charged? So this involves a little bit of thinking. Doesn't matter if you're wrong at this point. Have a think, see if you can pull some knowledge from other subjects about atoms to answer this question. So I'm going to give you 30 seconds to have a think. Okay, so let's see if we got this one right. So the answer is that atoms are neutral overall. We knew that. So if his experiment showed that there were negative particles inside the atom, but the atom's neutral overall, there has to be positive charge there somewhere. So the pudding part of the atom has to be positive to balance out that negative charge. So now we're going to move on to Rutherfords Model. I love this experiment. Obviously, I'm a complete nerd, but hopefully by the end of this, you will understand why I love this experiment so much. So this model was based on evidence that was provided by this very famous experiment that I love so much, that was carried out by his students Marsden and Geiger. Before we actually look at the experiment, we're going to play a game. There are some rocks on this screen. I would like you to tell me where they are. So, have you worked it out? It's pretty difficult to work it out because I've covered the screen up. So what I'm going to do is roll some marbles underneath the box. So little balls, I'm going to roll them under, and I'm going to show you the path they take. Okay, so we've got that one rebounded, got that one. Okay, so now that you can see the path that they took, do you think you could have a guess at where the rocks might be on the screen? Were you right? Okay, so let's have another go. So there is a mass under this box. I'll roll the balls, you guess where the mass is. Okie dokie, so have a guess. Where do you think the mass is on this screen? Okay, were you right? So we're going to go back to the history of the atom now, but remember this because it's going to come in handy later on. So, in 1908, Ernest Marsden and Hans Geiger were working with Ernest Rutherford in Manchester, which is in the UK. Marsden and Geiger were about to perform one of the most famous experiments in the history of science. In 1896, in Paris, in France, a discovery was made that was the key to unlocking the mystery of the atom. A metal called uranium was shown to emit a type of energy that could pass through solid matter like it wasn't even there. The scientists that were working on this at the time, they called it radioactivity. Rutherford was fascinated by radioactivity and he wanted to know everything he could about it. So with Marsden and Geiger, he came up with a series of experiments that would help him understand radioactivity better. The experiment was set up as shown. So we had a source of alpha radiation. So alpha radiation is a type of positively charged particle. And we had a zinc oxide screen. So this would fluoresce when radioactivity hit it. So the scientists bombarded a very thin sheet of gold foil with a beam of alpha radiation, and the screen fluoresced, as you can see here. So they used gold because it is highly malleable, so it's possible to produce sheets of gold that are only a few atoms thick, so the alpha particles would find it easy to pass through. So they wanted to know how the path of the radiation was affected by this very thin gold foil. As expected, the alpha particles went straight through the foil like it wasn't even there. Sometimes they'd swerve a little bit as they went through the foil, but they didn't think much about that. So Marsden and Geiger reported to Rutherford that they'd found nothing unusual. Rutherford then asked them to carry out the experiment again, but see if any of the alpha particles were bouncing back. So they did this out of scientific curiosity, just to work out and just see what happens. Any results that showed they didn't bounce back would still have been beneficial to the scientific community. So they set up the experiment again. So now we have this equipment. Again, we have the source of alpha radiation, and we have the screen coated with zinc oxide. And what we were expecting is the alpha particles would come, the beam of alpha particles would come through and hit the screen and fluoresce. Instead of all of the particles going through, this is what happened. Most of the particles went through, as expected. However, some were deflected through a small angle, and a very small amount were deflected through a large angle. So Rutherford was surprised and delighted by these results. He actually said that it was like firing a missile at a piece of tissue paper and have it bounce back at you. It took a long time, more research, more thinking. They eventually pieced together what was happening inside here. If the plum pudding model had been correct, this is the plum pudding model in case you'd forgotten, the alpha particles would have passed straight through. So the pattern they saw instead was this. Remember what I said about that game earlier and that it would make sense, okay? So where is the mass in this picture? Now if we flick back, where is the mass in this picture? So the mass isn't evenly spread out like it was in the plum pudding model. The mass is in the centre of the atom. And most mind-blowing of all, the atom is mostly empty space. So the reason I love this experiment so much is that the scientific curiosity, they carried out this experiment to just work out and see what happened. They got these really surprising results. They had to think about it, use evidence from other places and more research to piece together what's happening. It's a puzzle. Essentially, it's like a massive puzzle. So here are these results. What does it mean? Very cool. The really, really important thing that we have to remember when we're talking about this model and this experiment is that the alpha particles were deflected, not reflected. So the alpha particles never actually hit the nucleus. They were deflected away from it. This is Rutherford's nuclear model of the atom. We have a tiny positively charged centre where nearly all of the mass of the atom is found, and they called this the nucleus. And most of the atom is actually empty space. So the negative electrons are found in this yellow circle, this yellow area, but most of it's actually empty space. So here are the main points of Rutherford's nuclear model. So the atom is mostly empty space. The mass is concentrated in a central nucleus. The nucleus is tiny compared to the size of the whole atom. The nucleus is surrounded by a cloud of orbiting electrons. The atom has no net, which means overall charge, because the positive nucleus balances the negative electrons. And the electrons in the nucleus are held together by a strong electrostatic attraction. So remember, that means the attraction between a positively charged object and a negatively charged object. Okay, so classic exam question that you get for this would be the scientists, Rutherford, Marsden and Geiger, fired positively charged alpha particles at a very thin sheet of gold foil. They then measured the different pathways taken by the alpha particles. Describe and explain the pathways taken by those alpha particles. With a question like this, there's often a diagram to go with it. It might look a bit like this. So we have an alpha source, we have some gold foil, and then we have the alpha particles and their pathways. Okay, so I'm just going to pop that up here. Okay. What we need to do is describe and explain the pathways. Let's have a look at the first pathway together. Okay, we have to describe that. So if we think back to what we were talking about before, how many of the particles did this and what is the sort of pattern that they are taking? Most of the alpha particles went straight through the atom. Okay, so now that we have our description, we need to now explain why. So what was it about the atom that meant most of the particles were able to go straight through? I'll give you a couple of seconds to think about that. Okay, so our explanation is that because most of the atom is empty space, so most of those alpha particles were able to pass straight through because there was nothing there to stop them. Okay, so let's have a look at our next pattern. So let's see if you now can have a go at doing a description and an explanation. So mention how many particles there were, try and think back to what I said before, and then describe, so how many there are and then what kind of angle that was. I'm going to give you a few seconds to think about it and get your explanation down. Okay, so this is our description. So some alpha particles were deflected through a small angle. So most of them went straight through and some were deflected through a small angle. So that's the description of that second pathway. Now have a think if you didn't before. You've got 2 seconds to write your explanation. So think about what's happening. Think about the alpha particle. There's a hint in the question. It talks about one of the properties of an alpha particle. Think of the model of the atom. What would cause the alpha particle to be deflected like that? Remember, they do not touch the nucleus. So what is it? They're not bouncing off. They're not being reflected. Remember, they're being deflected. Okay, so the reason they were deflected through a small angle is because they were repelled by the positively charged nucleus. So up there at the top it says they fired positively charged alpha particles. The clue was in the question there. The positive nucleus is repelling some of those alpha particles as they go past. Okay, so we have the last one now. So this, have a go. You have a go straight from the beginning. See if you can describe and explain all in one go. I'm going to give you just over 30 seconds. Okay, so a very small number of particles were deflected through a large angle, and the reason for this is because the atom contains a very small nucleus where the mass and positive charge is concentrated. So the mass and the positive charge is concentrated in this tiny, tiny central nucleus. So only a very, very few alpha particles are going to be aiming or heading straight for that nucleus in order to be deflected backwards through a large angle. Remember what Rutherford said? This is like firing a missile at a piece of tissue paper and having it bounce back at you. You wouldn't expect that to happen at all, obviously. So only a small number of these alpha particles this is happening to because the nucleus is so little. Okay, excellent. That is such a classic question, and you guys have smashed it. This is the other question that comes up, not just on Rutherford's work, but on any kind of modelling question. So scientific models, and it could be about any of the models. So why did the work of Rutherford and Marsden convince scientists that the plum pudding model needed to be replaced with a new model? So I could replace the names of the models in this with any model. And you don't actually need to know anything about the model. It's not asking you to describe the plum pudding model. It's not asking you to explain the deflection of alpha particles, nothing like that. What it is asking you is, why do we sometimes replace one model with another? So think back to the very beginning of this video when I was talking about models and I was talking about why we might replace models. I was wittering on about theories and had a bee in my bonnet about people saying just a theory. What did I say about what makes us replace things? I'm going to give you 40 seconds to answer this one. Okay. Many measurements were taken, which means the data was reliable. I told you before that Rutherford repeated the experiment. He went away, did some more experiments, tried to gather more information. So the more measurements you take, the more reliable your data is going to be. So that's a really important point. The second one, if you didn't remember, was this. new evidence. It provided new evidence that could not be explained using the plum pudding model. So I could have used the names of two models. You didn't need to know it. You just needed to know a little bit about the scientific method and the process. Let's go back to our timeline. Rutherford developed the nuclear model of the atom. He presented it in 1911, and it was based on the evidence provided by the experiments carried out by his students, Marsden and Geiger. So Geiger is of the Geiger counter fame, so that machine that clicks a lot in films about radiation. Here we are with Niels Bohr now. He was a Danish scientist and he worked on Rutherford's model of the atom to improve it. So if Rutherford's model, so here we have Rutherford's model, and if it were completely correct, the electrons would actually lose energy and spiral down into the nucleus. So this would make every single atom unstable, which is clearly not true. So to fix this problem, Bohr modified the Rutherford model to show the electrons in shells. So in the Bohr model, the orbits of the electrons have a set size and energy level. The energy of the orbit is related to its size. So the smaller the orbit, the lower the energy level. And the orbits become larger as they get further away. They get larger the further away they are, and the larger the orbit, the larger the energy level. Okay, last little bit now of our history of the timeline. So more experiments by Rutherford and other scientists showed that the nucleus could actually be divided into smaller particles that had a positive charge. So they named these ones protons. And then about 20 years later, some experiments carried out by James Chadwick provided evidence of a neutral particle in the nucleus of atoms. So these are now called neutrons. If you'd like to know a little bit more about the discovery of neutrons and the discovery of protons and the experiments that were carried out, please have a look at the nuggets that are on Century. I will show you how to search the courses for the nuggets that you want a little bit later on, so you can have a look at that, get a little bit more information about how that was done. So here we have the timeline of the atom. So the current model of the atom is actually very like the Bohr model, but the electrons are moving too unpredictably and too quickly for us to know exactly where they're located. So we can, however, sort of make a good guess. We can say where they are likely to be in the atom. So here is our model of the atom that we know and love now. So we have the nucleus where the protons and the neutrons are found. We have the electrons orbiting that central nucleus. Most of the atom is empty space. The electrons are in shells. The energy levels are lowest, closest to the nucleus where they're smaller, and the energy levels are higher, further away from the nucleus where the shells are larger. The electron shells are sometimes called energy levels. They are also sometimes called orbitals. So don't get confused, it's just pretty much the same thing. And there you go. Okay, let me just swap my screen over. Okay, so Century analyses the areas that you're good at and the areas that you aren't so good at yet. And then it recommends what you should study next so that you can get better. It does this using artificial intelligence, and when you log in, you'll have a recommended pathway that looks something like this. So you can see Alison's recommended path, and these circles are the mini lessons on Century, so we call them nuggets. If you want to know why a nugget is appearing in the pathway, have a look at this little symbol here. So you can see whether a nugget is a diagnostic. So this is to figure out your baseline knowledge of a subject. The nugget could be chosen by the AI as something you need to focus on to improve, or it could be a memory boost or a revision nugget. Now today we're not actually going to follow this recommended pathway because we have been learning about the history of the atom. So what we are going to do is go to the courses page so that we can find the nugget that we were looking at. So this is a new course. You won't have it assigned to you yet because this is a sneak preview, but it is coming to you very, very soon. If you have Century already and you have the GCSE Essentials course or the GCSE course, topics, there are nuggets on this topic. So you do have things that you can be doing. So remember what I said, that I was merging lots and lots of lessons together for History of the Atom to make one big topic with lots of information in it about all the different things that happened through the development of the model of the atom. So for this, if we type in atom to search for what it is that we want, we can see here, history of the atom, a timeline. So we also have broken it down so you have everything that you need on all the different models. So if I search for plum, here we go. So we've got the plum pudding model, we've got the plum pudding model versus the nuclear model, often asked about in exams. If I pop in Rutherford, we will get that one. So there are all of these nuggets are in here so that you can use those to get a little bit more detail, go back over things, make sure that you understand each and every section. So we're going to pop into history of the atom, a timeline. Okay, so inside each of the nuggets, if you were learning by yourself, you would find the learning material that we have here. So we can go through all of the things that we've just talked about. So it would be similar to what we've just done. And if you were just revising the topic, you may want to look at the slides instead. Or you could just go straight ahead and try the questions. So today we've just done this topic, so we're going to go straight into the questions. So let's have a look at this one. Okay, so which of the diagrams below shows the plum pudding model of the atom? So we are going to go, we're going to go for B. Excellent. So we have got that one correct. So which of these diagrams shows the Bohr model of the atom? So this one's a little bit trickier. So we have to think about the different models that we just looked at. Okay, so I am going to get this one wrong, just to show you what happens when when you do get a question wrong. So this one that I went for is actually the Rutherford model, so it can be confusing to tell them apart. The electrons are not at set distances from the nucleus in shells in the Rutherford model. So that's how you would identify it. So it would have been C. I'm sure you're all shouting at your screen right now. And you are able to use these. So I've still got 3 reveals left for today. So I'm going to click on this and it will reveal the correct answer for me. So there, if I wanted to use that, I could. The other option would be to go back through the slide. So here we are, we're looking for the Bohr model. So let's have a look back at the slides. I mean, the sensible thing would have been to do this before I got the question wrong, but you live and learn. So here is the Bohr model. It's telling me it's got them in a set energy level. They're in shells. The orbits become larger as they get further away from the nucleus. So I could have used that information to help me answer the question. So which of the diagrams shows Dalton's model of the atom? I'm going to learn from my mistake. I'm going to go back here. Okay, so it is a solid sphere like this. So I'm going to go back. And the one that is a solid sphere is B. Excellent. Ta-da. Okay. Okay guys, I'm going to go back to the slide now with the information on there for signing up to get a Century account if you don't have one already, so that you have a little bit more time to write that down if you want to. It was lovely to see you guys today and I hope you enjoy the rest of your day. Thank you very much. Bye-bye.